morning. This is a Mod-04 discrete time Markov chain, lecture 6, time reversible Markov chain, and then application of irreducible Markov chain in queuing models. So, in this lecture I am planning to give the time reversible Markov chain and how to compute the stationary distribution in a easy way. Then I am going to give applications of irreducible Markov chain in queuing models. Here irreducible Markov chain means it is a DTMC model, because later we are going to give the applications of irreducible continuous time Markov chain in queuing models also in the later lectures, and also I am going to give few simple examples. What is the meaning of a time reversible Markov chain? First, let me explain how to construct the time reversible Markov chain. Consider a DTMC, it is of course a time homogeneous discrete time Markov chain. You see the collection, it is in the usual way xn minus 2, xn minus 1, xn plus 1, xn plus 2 and so on. Now, you trace the DTMC backwards. That means, you know the first all xn plus 2, then xn plus 1, then you know what is xn, then you collect xn minus 1, xn minus 2 and so on. Now, the question is whether if you make a DTMC backwards and that sequence of random variable, that is of course, it is a stochastic process, whether this is going to be a DTMC. Any stochastic process is going to be a DTMC if it satisfies the Markov property and the state space is discrete and the time space is also discrete. But if you see this the DTMC backward, that is also going to satisfy the Markov property. The way the given situation, the future depends only on the present, not the past history, that is a Markov property. The same thing is going to be satisfied in the reverse also. The Markov property is satisfied by the reverse, the backward DTMC. Therefore, this is also going to be a time homogeneous discrete time Markov chain. Now, I am going to define what I am going to give, how to find out the one step transition probability for the reversible process, that you take it as the matrix Q that consists of elements Q I J. You can find out the entries, the Q I J, that is nothing but what is the probability that the system will be in the state J at the nth step, given that it was in the state I at the n plus 1th step. That is different from the original DTMC. The original DTMC, it is what is the probability that the system will be in the x n plus 1 in the state J, given that x n was I, whereas here it is x n is equal to J, given that x n plus 1 is equal to I. This conditional probability you can compute in this way: the product of probability of x n is equal to J multiplied by the probability of x n plus 1 is equal to I, given that x n is equal to J, divided by what is the probability that x n plus 1 is equal to I. That is same as the probability of x n is equal to J is nothing but in a steady state, what is the probability that in at the nth stage in the system will be in the state, that is equal to pi j multiplied by what is the probability that this is the one step transition probability of system is moving from J to I, divided by pi I. That means the Q I J is going to be pi j P j I divided by pi I, assuming that the stationary distribution exists. Otherwise, pi j is equal to limit n tends to infinity of P I j n. Now, I am going to give the definition of a time reversible. A DTMC is said to be a time reversible DTMC if both the transition probabilities are one and the same. That means the one step transition probability of the new or the time reversible process Qij is same as what is the one step transition probability of the original DTMC, that is Pij. That is, the reverse DTMC has the same transition probability matrix as the original DTMC. Now, I am going to equate this, the Qij is equal to this much. Therefore, that is same as pi j of Pji is equal to pi I of Pij. And if this equation is going to be satisfied, then that DTMC is going to be called it as a time reversible Markov chain. And this collection of equation for all Pij, that equation is called a time reversibility equations. Now, I am going to give the few results on time reversible Markov chain. Let me take a irreducible DTMC. If there exists a probability solution, that is a pi is the vector, satisfies the time reversibility equations, that is the vector pi consists of pi 1, pi 2 and so on. So, if that entries satisfies the time reversibility equations, that is pi I is equal to pi I times Pij is equal to pi j Pji for all pairs of I comma j, then the DTMC has a positive recurrent states and also it is a time reversible, and the solution pi is a unique stationary distribution. That means whenever you have a irreducible DTMC and if you have there exists a probability solution vector pi satisfies the time reversibility equation, then we can conclude that DTMC has a positive recurrent states as well as that DTMC is a time reversible Markov chain. Also the vector pi that satisfies the time reversibility equations, that vector pi is a unique stationary distribution. So, the how one can use the time reversible concept in finding the stationary distribution, that I am going to explain in the next example. Let me take a simple example which consists of 4 states. It is a finite model, finite state space. Also it is irreducible because each state is communicating with each other states, and I assume that the probability p that is lies between 0 to 1. Therefore, this is going to be a periodic states. So, this Markov chain is a finite, irreducible, and you have the result for a finite irreducible Markov chain, at least one state is going to be a positive recurrent. So, since it is irreducible, all the states are of the same type, therefore, all the states are going to be a positive recurrent states, and also it is a periodic. So, you can use the result of irreducible, a periodic, a positive recurrent and also the finite states going to give the unique stationary distribution, and that can be computed by solving pi p is equal to pi, where pi is the stationary probability vector. Here you can use the time reversibility concept. Therefore, you do not want to solve actually pi p is equal to pi, but you can start from the time reversible equation. From that you can get the solution. That is what I have done it in this example. First I have checked it is irreducible, then I check whether the time reversible equation is going to be satisfied by this irreducible Markov chain. So, since it has the 4 states, I am just checking all the states whether the time reversibility equations are going to be satisfied. That is satisfies. Since it is you see the previous result for a irreducible DTMC, if there exists a probability solution, that means I started with there exists a solution, but since I know the result, it is a irreducible, a periodic, positive recurrent, and the stationary distribution exists. Therefore, I started with the probability solution pi, and I have checked it the time reversibility equations for the example also. Then I am concluding it is going to have a unique solution. So, I have checked. I have verified whether I have verified the time reversibility equations. After the time reversibility equations, from that I am getting the pi n in terms of pi naught, because the way the recursive relation goes, you can make out pi 1 from the first equation, you can get pi 1 in terms of pi naught. Then the second equation pi 2 you can get it in terms of pi 1, then in turn you can get pi 2 in terms of pi naught. Similarly, you can get pi 3 in terms of pi naught. Now, you have to find out what is pi naught. Pi naught, you can use the normalization equation, that is a summation of pi a is equal to 1, that is pi naught plus pi 1 plus pi 2 plus pi 3, that is equal to 1. From that you can get pi naught is equal to 1 divided by 1 plus p divided by 1 minus p, p square by 1 minus p whole square plus p cube by 1 minus p whole power 3. So, this is going to be the pi naught. Substitute pi naught in this pi n, therefore, you get the pi n also. So, we are getting the unique stationary distribution, because this DTMC is a time reversible. Therefore, without solving the pi p is equal to pi, you are using the time reversibility equation itself, and summation of a pi a is equal to 1, you are getting the pi a's. So, that is a easy way whenever the DTMC is going to be a time reversible Markov chain. Now, I am moving into the applications of irreducible Markov chain in queuing models. Yes. So, in this example, we have used time reversibility property to get the unique stationary distributions. In the result, we said there is a, and the solution pi is a unique stationary distribution. So, in the results needs only the proof whether the pi is going to satisfy the equation pi p is equal to pi. So, that can be easily proved by taking summation of pi i's p I j, that is same as summation over I pi j of p j I, because it satisfies the time reversibility equation. We can write a summation over I pi I times p I j same as a summation pi j p j comma I. That is same as, you can take out the pi j outside, that is same as the summation over I the p j I. And you know that the summation over I the p j I, that is going to be 1, therefore, this is going to be a pi j. So, hence we get summation over I the pi I of p I j, that is equal to pi j. So, this is nothing but in the matrix form pi p is equal to pi. So, whenever you have a irreducible DTMC and satisfies the time reversibility equations, then you have a unique solution pi, and that pi unique solution is a stationary distribution. So, and also you can prove easily it has the positive recurrent state and the time reversible Markov chain also. So, with this proof, we have got the result that the pi is going to be a unique stationary distribution, and also I have given the example how to use the time reversibility equations to get the unique stationary distribution. Now, we are moving into the application of irreducible Markov chain in queuing models. For that I am going to start with the one example. Through that I am going to explain the queuing models, and later also we are going to give the application of a irreducible continuous time Markov chain in queuing models, and this is for the discrete time Markov chain. You see the example. Consider a barber shop with a fixed capacity of 6 people, including the one whose hair is being cut. Hair is being cut. Observation indicates that in the time required to cut one person's hair, there may be 0, 1 and 2 arrivals with the probability 0.3, 0.4 and 0.3 respectively. Any new arrival is denied entry when the shop with the 6 people. Find the long run proportion of time that the shop has 6 people in it. So, here we have given only few information, that is there is a barber shop and which has the maximum capacity 6 people, including one is getting the haircut. That means at any time the number of people getting the haircut will goes from 0 to 6, and when during the haircut time there is a possibility no one can arrive with the probability 0.3, or there is a possibility one person can arrive during the any one person's haircut, that probability is 0.4, and also there is a 2 people can arrive during one person's haircut, that probability is 0.3. And whenever the system is with the 6 people already there, that means one is under haircut and the remaining 5 people are in the waiting, then the whoever enters, it cannot be enter into the system, it will be always denied. The question is, what is the probability that in a longer run the system will be in the state 6. So, this can be analyzed with the queuing model, and for that we need a first stochastic process. So, the stochastic process we need a random variable. So, the random variable is here x t denotes the number of customers in the barber shop at time t. For fixed time, how many people in the system, that is a random variable. Therefore, over the time if you collect, then that is going to be a stochastic process, and this stochastic process is the continuous time discrete state stochastic process. This x t is a x t is a continuous time discrete state, because the possible number of customers in the system that will goes from 0 to 6. So, this is a continuous time discrete state stochastic process. The corresponding queuing model, it is a MG16 system. This is a one way of visualizing this as the MG1 system, like that you can visualize in a different way, but the queuing system, how one can define. Now, let me explain that. The queuing system is a system in which the customers are getting served and leave the system. Here the people who is entering into the barber shop, that is going to be the customers who are entering into the system, and the system is nothing but the barber shop, and the haircut is nothing but the service time, and whenever the haircut is over, then it leaves the system. So, this can be written in the Kendall notation with the first letter is denotes for what is the inter arrival time distribution, slash second letter that is denotes for what is the service time distribution, slash the third is denote how many servers in the system, the fourth one what is the capacity of the system, that is what is the maximum number of customers can be stay in the system, stay as well as getting the service, and the fifth one is nothing but what is the population of the input source, that is usually make it as the infinite, therefore, we will not write it here, I did not write it here. And the next one is what is the service discipline. Here the default is a first come first served. So, that also we will not write if it is a default. So, the default input source capacity, that is infinite, and the default service discipline is a first come first served, that also we will not write. Whenever it is changes, then we will write down in the notation. So, here this is the MG-16 system, because the inter arrival time that satisfies the Markov property, that is the assumption we have taken here. Therefore, it is a M denotes for Markov property is satisfied, or the inter arrival time distribution is exponential distribution. The G is for service time distribution, which is general here. If the service time distribution is exponential, then we write M there, because the Markov property is satisfied. In this model, we have only one server, therefore, the third letter denotes 1. The fourth is the capacity, the system capacity here, that is 6. The capacity of the system means maximum number of people can wait in the system, and the person who is getting service. So, here the capacity of the system is 6. Like that we can give many more examples. So, here I have given M/M/1, that means inter arrival time distribution is exponential, then service time is exponential, which is independent of the arrival, and only one server in the system. Since the fourth letter is not here, that means it is a default, the default capacity of the system is infinite. The second example is a MM14, that means similar to MM1 system, but here the capacity of the system is 4. The third example M/M/infinity, that means it is inter arrival is exponential and service is exponential, whereas the number of servers in the system, that is also infinite. That means it is sort of a self service discipline. Therefore, the customer himself act as a server. The fourth example, that is M/M/3/7, that means it is 3 servers in the system and the capacity of the system is 7. That means at most 3 people can get service and at most 4 people can wait in the system. Therefore, the maximum capacity or the capacity of the system, that is 7. So, I have given a very simple way of explaining the queuing system, but in this example we have I have explained how the queuing system is attached with this problem and I have given the interpretation, but later we are going to give the different type of queuing models, which is going to be the application of irreducible continuous time Markov chain, that will be the later. With this, the information given in this problem, I can go for writing another random variable, that is x n, x suffix n, that is nothing but number of customers in the shop at the completion of the nth customer's haircut. This is also going to be a stochastic process, because over the n I can collect the random variables and that will form a stochastic process, but this stochastic process is going to be a discrete time, discrete state stochastic process, because at the completion of every customers you will find maximum 5 customers in the system behind him. Therefore, the possible state space, the state space is going to be 0, 1, 2, 3, 4 and 5. This stochastic process, that x n, is embedded in the stochastic process x of t. The x of t is a stochastic process, that is a continuous time discrete state stochastic process, whereas x n you are observing the system at the completion of a nth customer's haircut. Even if you can say it is after the nth customer's leaves, excluding him, how many customers in the system, that is going to be the state space. So, you are observing the system at the completion of the first customer, then second customer, then third customer and so on. Therefore, this is embedded in x of t. Therefore, this stochastic process is called embedded Markov chain. Why it is Markov chain? You can verify the x n, the stochastic process x n, x suffix n, n is running from 1, 2 and so on, and this is a stochastic process, and this stochastic process is going to be a embedded Markov chain. The reason is this is a stochastic process and also satisfies the Markov property. That means what is the probability that the system will be in some state in future, given that you know the state at the present as well as the past, that is same as what is the probability that the system will be in the future in some state given the present, not the past. So, that Markov property is going to be satisfied for this discrete time discrete state stochastic process. Therefore, this is going to be a Markov chain. So, the x n is a DTMC. Since it is embedded in x of t, this is called a embedded Markov chain. I am not giving the Markov property how it is satisfied, but one can analyze, because the arrivals are IID random variables. Whenever how many customers are entering into the during the one's haircut, whether one customer is entering, 0 customer is entering or 1 customer is entering or 2 customer is entering during the one person's haircut. If you assume all the arrivals are IID random variables, then whenever you see the completion time and you collect those completion time, those random variable, and that random variable satisfies the Markov property. Therefore, this is called the DTMC and also call it as a embedded Markov chain. Now, we can find out what is the one step transition probability for this embedded Markov chain that I have presented here. That is a P matrix, because the possible states are 0, 1, 2, 3, 4 and 5. Therefore, I have written the 6 cross 6 matrix, and the entries are, first let me explain what is the probability that the system was in the state 0 when. So, before explaining the P matrix, let me give the trace, then after giving the trace or sample path, then I will come back to the one step transition probability matrix, because through the sample path or trace one can easily visualize how you can get the entries of a one step transition probability matrix. See, this is a sample path, you know the meaning of sample path. This is a one possibility, like that you can go for many possibilities. This is called a sample path or the trace. So, over the time, so I have made it wrongly. So, this is over the time, and this is the number of customers in the system at time t. So, the A suffix 1 denotes the first arrival, the A2 denotes the second arrival with the probability 0.3, the possibility of no arrival, or with the probability 0.4 1 arrival, or with the probability 0.3 2 arrivals. So, here the A2 denotes the second arrival, but that is the 2 arrivals together, therefore, the system goes from 1 to 3, whereas the service is 1 by 1. So, the D1 denotes the time at which the first customer leaves the system, that is the first departure. So, departures are with the notation D's and A's for the arrival, and at the time of D1 you are observing the system, therefore, that is x suffix 1. So, how many customers in the system at the time point D1, that is how many customers in the system at the completion of the first customer leaves, that is that denotes the x 1. So, since there are 3 customers in the system, initially 1, then 2 more customers enter, therefore, the total number is 3 and 1 leaves. So, when he leaves, he will see 2 customers in the system. So, x 1 is 2. X 2 is the second customer departure. When second customer departure, already 1 will be there. So, x 2 is equal to 1. During the second customer, see, during the first customer there are 2 customers entering into the system, whereas during the second customer's service no one arrived. Therefore, the D3 is the third customer leave the system and X3 is the number of customers behind him when the third customer leaves. So, that is going to be 0, and you will not bother when the A3 comes and A4 comes and so on. The next the embedded Markov chain, that state, that random variable is x4, that is when the fourth customer leaves. So, you will not bother when the A3 third arrival comes or the fourth arrival comes, whereas here the D4 is now there are again 2 customers enter into the system. Therefore, first one customer enter into the system and during his service another 2 customers enter, therefore, 3, therefore, x 4 is going to be 2, because when he leaves he will find 2 customers in the system. So, this is the possible values of x 1, x 2, x 3, x 4, and this is going to be the possibilities. So, this is a sample parts. So, now you would have explained, now you would have known how to, what is the value of x n's or how to get these values. Now, I am going to explain how we can get the entries of the P matrix. What is the meaning of 0 to 0, P 0 0. So, P 0 0 is nothing but what is the one step transition probability values. So, the P 0 0 in one step, that is nothing but what is the probability that the x n plus 1 is equal to 0 given that x n was 0. So, this is the one step transition probability for all n. For all n, what is the probability, what is the transition probability of system is moving from the state 0 to 0 from the nth step to n plus 1th step. That means when nth person leaves, when nth person leaves, he did not see anyone in the system, that means the system was empty after he leaves. When the n plus 1th person leaves, he also sees no one in the system behind him, therefore, x n plus 1 is equal to 0. So, what is the transition probability of the system is moving from the state 0 to 0 at the end of nth completion time, nth customer completion time, and at the end of n plus 1th customers completion time. That means, during the n plus 1th customer's arrival time, no one enter into the system, and you do not want to bother what time the n plus 1th customer enter into the system, that is immaterial, because we are considering only the completion time or the time epochs at the completion time. Therefore, this is nothing but, this situation is nothing but no one enters during the n plus 1th customer's haircut. That probability you know, that is the given. So, that probability is a 0.3, that means 0 customers enters during one person's haircut, and here we assume all the persons are identical and all the arrivals and so on, all are IID random variables. Therefore, here whether it is a n and n plus 1 and so on, for all n it satisfies. Therefore, this probability is 0.3. Similarly, you can go for what is the probability of system is moving from the state 0 to 1 in one step. That is nothing but what is the probability that x n plus 1 will be in the state 1 given that x n was 0. That means, when nth person leaves, he did not find anyone in the system was empty. When n plus 1th person leaves, he find 1 behind him. That means, when the nth person leaves, no one in the system. Therefore, the n plus 1th person would have arrived at some time. During his service, there is a possibility of one customer's entry into the system. Therefore, when he leaves, he finds the person who enters during his haircut. That means, what is the probability that one customer enters during one person's haircut? That probability is 0.4. So, that is this one. Similarly, you can go for finding out what is the entity of P02. P02, that is nothing but the system is moving from the state 0 to 2 in one step. That is nothing but 2 persons would have arrived during the n plus 1th customer's haircut time. So, that probability is 0.3. The other possibilities are not possible, because we have either 0 customer or 1 customer or 2 customers can enter into the system. Therefore, the other probabilities are 0. Now, we will move into the second row. What is the probability that the system goes from the state 1 to 0, 1 to 1, 1 to 2 and so on. This also can be discussed in the same way which I have explained in the first row. Here, when he leaves, he has seen one person. When the nth person leaves, he has seen one person. Therefore, the system was in the state 1, and when the n plus 1th customer leaves, what is the probability that he sees no one in the system? That means, during the time no one arrived. During the haircut time no one arrived, therefore, that probability is 0.3. Now, when the nth person leaves, he saw one customer in the system. When n plus 1th customer leaves, he also saw one person in the system. That means, during his haircut time 1 is arrived. So, that probability is 0.4. Similarly, you can go for the system going from state 1 to 2 in one step, that is going to be the 0.3, and all other possibilities are not there. Therefore, that probabilities are 0. Now, we will come to the state that is corresponding to P20. 20 means, when someone leaves, he saw 2 people. When the next person leaves, he saw 0 people. That is not possible, because one by one we are taking a random variable x n plus 1 and so on. Therefore, there is no way when the next person leaves, he cannot see 0 people in the system, because after the service is over, then only he can leave the system. So, therefore, the system going from 2 to 0, that is not possible, that probability is 0. Whereas, the system is going from the state 2 to 1, that is possible. That means, when nth person leaves, he saw 2 people. When n plus 1th person leaves, he saw 1 person. That means, during his time no one arrived. So, that probability is 0.3. Then 0.4 and 0.3, the same way you can go for the argument for the other rows. The last row is again important. The system going from the 5 to 4, that means, one decrement, that is because of no one arrived, therefore, that probability is 0.3. Whereas, the system is going from the state 5 to 5, when the nth person leaves, he saw 5 people in the system, that means, the system was full during the nth person's haircut time. Therefore, since the capacity is 6, that means, maximum 5 people can wait and 1 person is under service. Therefore, when the system is in the state 5, at the completion of nth person's haircut, that means, the system is full. So, if during his haircut time, if 1 people or 2 people arrived, if the 2 people arrived, then still the system will be in the system 6 only, not more than that. Therefore, the possibility of the 1 person arrived and the possibility of 2 persons arrived, still the system will be with the maximum capacity 6. Therefore, when the nth person leaves, he see 5 people. When the n plus 1th person leaves, he will see again 5 people, either because of 1 person arrived during his haircut or 2 people arrived during his haircut. So, you have to include both, therefore, 0.4 plus 0.3, therefore, it is 0.7. You can verify all the row sums, that is going to be 1 and the entities are 0 to 1. So, this is the one step transition probability matrix corresponding to this problem, and this problem has a embedded Markov chain. And the original stochastic process is a number of customers in the system at any time t, and that is a continuous time discrete state stochastic process, that is a non-Markovian model. But when you are making embedded, that means, we are finding the time epochs in which the Markov property is satisfied, and those time epochs at the completion of every haircut time, the Markov property is satisfied. Therefore, you will end up by embedded Markov chain, and this is the example, or this is the application of a discrete time Markov chain in the queuing model. And this is a DTMC because of the assumption of IAD arrivals. Now, you can verify whether it satisfies the irreducible property, because the way you have a Markov, the one step transition probability matrix, from that you can make out that this is each state is communicating with each other state, all other states, or you can draw the one state transition diagram and you can conclude it is a irreducible Markov chain. That means, you have a one closed communicating class, and each state is communicating with all other states, and that is same as the state space. So, the whole state space is same as the one closed communicating class. Therefore, this is a irreducible Markov chain. Next, aperiodic, you can find out this is a finite model, and it is a positive recurrent state, and you can find out the periodicity of the recurrent state. Since it has a self loop with a positive probability and so on, you can conclude the greatest common divisor of system coming back to the same state, that number is going to be 1. Therefore, this is a periodic irreducible, and also you can verify it is a positive recurrent. It is a finite model irreducible, therefore, it is going to be a positive recurrent, and you know the results for any irreducible aperiodic positive recurrent Markov chain. the stationary distribution exists, and that is going to be unique, and you can find out by solving pi p is equal to pi with the summation of pi a is equal to 1. So, you solve this equation because this is a homogeneous equation, you use in this normalizing condition, summation of pi a is equal to 1, you will get the vector pi with the entries values pi 0 to pi 5. Once you get the pi values, you can go for what is the question is asked. The question is find the long run proportion of the time this shop has the 6 people in it. So, here this is nothing but in a long run what is the probability that 6 people will be in the system. Suppose you analyze the system with the stochastic process x of t, then you would have got the long run proportion of the time, but that is same as we are using the result, that is same as if you study the embedded Markov chain, and that embedded Markov chain, the steady state probability, that is nothing but if you want to find out in the long run what is the probability that the system has the 6 people in it, that is same as in a longer run what is the proportion of the time the shop has 5 people at the end of the completion time. So, the steady state probability of 6 people in it, this is a long run proportional time, that is same as what is the stationary distribution in a, or the limiting distribution, the 6 people in it, that probability is same as at the time epochs, the completion time epochs, what is the probability that in a longer run 5 people in the system at the time epochs. Therefore, that is same as the pi phi, because this is a pi phi is the stationary probability that 5 customers in the system at the completion of the time epoch in a longer run. So, whatever you are getting the probability values for the pi phi, that is going to be the proportion of the time the system has 6 people in it in a longer run. So, this same example can be extended with the model called a MG1 queuing model, because this example is the MG16 model, whereas you can go for MG1 queuing model, and in this model also you have a embedded Markov chain that is related with the random variable x of x n, and that is going to be the same thing what is the or the number of customers in the system at the time epochs of completion of nth customer service. So, that is nothing but that is the x n, and that will form a discrete state discrete time stochastic process. Even though the service is going to be a non exponential distribution, whenever the service is completed and you see how many customers in the system, because the customers inter arrival time is a exponential distribution which is independent of the service time, and only one customer in the system, only one server in the system, and the first come first served service policy with the infinite capacity in the system, the Markov property is going to be satisfied at the service completion time epochs. Therefore, how many customers in the system after the service is completed, after the time at which the nth customer's service is completed, if you find out that random variable and collect those random variable over the customers x n for n is equal to 1, 2 and so on, and that random variable is going to, that stochastic process is going to be satisfies the Markov property. Therefore, that is called a discrete time Markov chain, and this is also embedded Markov chain because that is embedded in the stochastic process x of t. if you assume that this is going to be a irreducible, a periodic, and this also has the one step transition probability matrix P of the form with the entries k naught, k 1, k 2. Here the k naught, k 1, k 2, k 3s are similar to the number of arrival of customers in the system during the one person's service. So, that is so the k I is nothing but what is the probability that I customers arrived during the any nth customer's service. Therefore, since it is a embedded one, so the first row and the second row will be one and the same. Then you will get the other entries. Therefore, the way I have explained the previous example, that has the finite capacity model, the finite state discrete time Markov chain, whereas this is a infinite state space DTMC. Therefore, I have made it with the P matrix in this form. Our interest is to find out what is the stationary distribution. For that, I am introducing two generating functions. One is a P of S, that is related with the number of customers arrived during the nth customer. The other one is the stationary distribution, that is pi of S. If you see, I did not make the assumption whether it is a positive recurrent or null recurrent or transient and so on. So, here I made the assumption only it is irreducible. So, if the probability generating function P of S, if you differentiate then substitute S is equal to 1, if that value is going to be greater than 1, then all the states are going to be transient. If that value is going to be 1, then all the, since it is a irreducible, all the states are going to be a null recurrent. If the P dash of 1 is less than 1, then all the states are going to be a positive recurrent. You can cross check using the simple way of checking the positive recurrent, null recurrent by mean recurrence time is going to be a finite, the infinite also. So, if this is the condition, then you can classify the states as a transient, null recurrent or positive recurrent. Now, we make the assumption it is going to be a positive recurrent by satisfying the condition P dash of 1 is less than 1. So, since it is a positive recurrent, irreducible, and also I have taken a periodic. If it is not a periodic, then it is a different thing. So, I made the assumption it is irreducible aperiodic and satisfying the condition P dash of 1 is less than 1, therefore, it is going to be a positive recurrent. So, the unique stationary distribution exists. Now, we will explain, we will see how to find out the stationary distribution. You have to solve pi is equal to pi p, you know the P matrix. So, you take the first equation pi naught is equal to k naught pi naught plus k 1 pi 1. From this you will get pi 1, and the second equation you can get the pi 2 in terms of pi naught and so on. Instead of this you can use the generating function, that means you multiply S pi 1 S, the third equation you can make a multiplication of S square and you add, you will get the generating function. So, you will get the pi of S is equal to in terms of pi naught with the P of S. Use summation of pi a is equal to 1 to get the pi naught. So, you can find out pi naught by using this concept limit S tends to 1, the pi of S divided by pi naught is same as limit S tends to 1 minus S times P s divided by P s minus 1. So, you can get the pi naught, that is same as 1 minus P dash 1, and already we made the assumption P dash of 1 is less than 1, therefore, this quantity is going to be a positive quantity pi naught. Hence, you substitute a pi naught in the pi s expression, therefore, you will get the generating function for a stationary distribution. And by taking the Once you know the generating function, you can get the probabilities. And this stationary distribution in terms of PS, and you know what is PS also, because the number of arrivals, that probability is given, therefore, you know the probability generating function for the arrivals also. So, you know PS, using the PS you can get the generating function for the stationary distribution, therefore, you can get the probabilities. As a summary, we have finished the time reversibility Markov chain, and we have explained the embedded Markov chain also, and I have explained the queuing system, and I have also given the simple examples, and these are all the reference books for this lecture.